from the University of Calcutta. He has currently working as an associate professor in the Department of Avionics, Indian Institute of Space Science and Technology, Department of Space, Government of India. He has visited several international universities of reputed like Royal Military College of Canada, Queen's University, and in 2015 to 18 in various capacities, and having collaborative research with the RMC Canada, Kingston, Orentino University, and many more. He is a senior member in IEEE, senior member of International Union of Radio Science, and life member of IETE. He is the founding and current chairman of IEEE MTTS Kerala chapter. He served as a chairman of Antenna and Propagation chapter of IEEE Kerala section during 2018 and 19. Dr. Saha has received several prestigious awards, which includes our Visvesvaraya. I will just read that to confirm it. So it's a best certificate of excellence for the AICT Visvesvaraya Best Teacher Awards in 2021, and Outstanding Teachers Award in 2019, Department of Avionics, IIST, National Scholarship from Ministry of Human Resource Development from Government of India, Outstanding Award, Outstanding Contribution Award from the APMTT Calcutta chapter, Best Contribution Award for Noctil service and significant contribution towards the advancement of IEEE and engineering professions. He is also the board reviewers of several international journals and reputed IEEE transaction journals. His area of expertise includes energy harvesting, channel modeling for WB, UWB system, microwave circuit, engineering materials, metamaterial inspired antenna, and circuits, reconfigurable and multifunctional antenna for modern wireless application. So I just want to deliver this platform to Chinmay sir, so we can learn something from him, sir.
Yeah, I just want to add one more award, that is IET Professor SN Mitra Memorial Award 2021. So congratulations, sir, for these two awards in 2021, Best Teacher Award and this IET Professor SN Mitra Memorial Award. And we are honored that you are accepted our invitation to deliver the lecture.
Yeah, thank you very much. At the outset, before I start, I would like to thank the organizers, especially Dr. Mishra, Dr. Chandan, who are the coordinators for this particular event, and also all other people like Dr. Soni, the Dean of the Institute, and if I don't forget the name, probably I'll use the flyer, your Chief Patron, Professor Alok, then Patron, Professor Shailendra, Professor Arjunan, Mrs. Anita, the coordinators of the event, as I mentioned, Dr. Mishra and Dr. Chandan. And I understand that there are other people also involved at the background whenever we do have an event of larger magnitude. Am I properly audible?
Yes, sir.
Yeah.
Yes, sir.
So I understand that a lot of people are there in the background for organizing such an event, and I congratulate all of you for taking this initiative. And also at the outset, I again thank you for for elaborate introduction and showing the video that was just a couple of weeks before receiving the award from Union Education Minister, and incidentally AICT Chairman, AICT Secretary, Secretary of Government of India Education Department, everyone was there, so it was a big occasion. And yeah, so with this brief introduction, and again thanking all of you and all the participants and welcoming all the participants, let me go into the agenda and go into the detailed presentation. So when Dr. Mishra invited me for this one, I in fact gave him 3-4 options, like which topic you would like to be offered by me. In fact, I was thinking that I talk on some other topics, not the one that I am going to talk now, because I have talked on this topic quite a few times. So maybe there are a few attendees who have already listened to this one, but there is always changes because science, engineering, technology is always changing. So over last 1 year, there have been some new work that also we have done. So I'll try to cover those also, but some part will be cross-section, having some cross-section with my previous talks. So those who have attended my previous talk, you may, think deeper and ask me more thought-provoking questions. Okay, so with this, let me share my screen. Do you see my screen?
Yes, sir.
Yes, sir.
Yeah, so you have prepared a very beautiful flyer. So I just cropped the top part of the flyer and have accommodated in the first slide. And I'll be talking on metamaterial inspired antennas for modern wireless applications, concepts, and state-of-the-art techniques. So this is a topic which is very close to my heart because I started even my PhD journey with this in 2005-06. Even I did some of my MTech thesis work in that particular direction before that. And then it has been almost a journey for more than 15 years. There has been a lot of innovations, a lot of new ideas, new concepts, and quite a few PhD students also have worked on this, and I have collaborated with even some of the foreign universities, other Indian institutes also, especially IIST Bangalore over last few years. So this is a long journey, so I'll try to give glimpses of all the aspects, all the applications especially, but I'll also start from the very basic, very fundamental physics of metamaterial, because I understand that AICT ATAL initiative is a great initiative, and they actually want these talks to be a resource and it will be used for generations. While going to Delhi last week for this award, in fact, I visited the AICT ATAL director and other people involved, and in fact, I mentioned about this particular event and other AICT ATAL initiatives where I have been a speaker. So what I understood is that this is a sustained initiative, and this is going to be very, very useful for next generations, etc. So concerning that aspect, I'll cover the fundamentals also. So this is a very brief about my institute, IIST, as you know, Indian Institute of Space Science and Technology. We started our journey in 2007 under the leadership of Dr. APJ Abdul Kalam. He was the founder chancellor of the institute. The basic idea was to produce quality human resources for Indian Space Research Organization. And we have supplied, or we have rather graduated more than 1,000 engineers who are working in different centers of ISRO as of now. And apart from that, we have masters, PhD, different projects with different organizations, especially very strong relationship with different ISRO centers. So this is a little bit info about my institute. In my department, at the Department of Avionics, we have undergraduate in avionics, or we call it electronics and communication engineering now. And we have 5 different disciplines of MTech. And I'm the course coordinator for MTech in RF and microwave engineering. So if you have any question related to IIST or any other opportunities, that also you can feel free to ask me. And before I go into the agenda, let me give you some ideas regarding the research activities that we do in our research group. So predominantly our activities can be classified into these three. We are involved in doing printed antenna research, and under that different kind of antenna designs and applications we have considered, starting from printed to SIW to dielectric antennas, dielectric resonator based antennas for various applications. And then being part of Department of Space, we have a mandate of doing work related to space science, space technology, space engineering, and also having a very good rapport with different centers of ISRO. We are involved with different kind of antenna design. In my research group, we are very much involved with National Remote Sensing Center, Hyderabad. We have collaborated successfully and we have designed some antennas, ground station antennas for upcoming mission applications, because in future the current X-band data receiving system will be replaced by multi-band data receiving system because of more bandwidth requirement and high data rate that is sent from the satellite. And apart from that, we have designed some conformal antennas for reachable launch vehicle applications. And this is another wing of our research, which involves millimeter waves, wireless power transfer, and terahertz systems. So micro circuits, different kind of passive components, wireless power transfer, wireless energy harvesting. Couple of PhD students are working on that area. And in fact, we have extended further towards the sensors, optical fiber based biosensors for different kind of applications. So this is in a nutshell what we are doing and what we have done. And I'll spend another couple of minutes on some of the research highlights of our group. So I'll be going into details of some of those things very soon. So these are some designs related to printed antennas. This is some kind of ultra-wideband printed antenna, which is basically a printed monopole antenna, which is loaded with certain kind of resonators for producing certain applications. All these materials are from our own publications over last 10 to 12 years. And then I'll be explaining these concepts in detail. Just hold on for me a few more minutes. And then we have worked on notched ultra-wideband antenna, where we have used the dual and multi-band application using a same monopole antenna by loading different kind of resonators on the feed line of the antenna. We have achieved such functionality. Not only that, I'll explain this concept in a very detailed fashion. Something which is very novel, and we are the first group to report that particular work, is a multifunctional antenna, a single antenna which can cater to multiple antenna functionalities. I'll be explaining in detail where a single monopole antenna, by combinatorial loading of different kind of resonators and switches in terms of pin diode or MEMS switches, etc., can invoke multiple antenna functionalities. So I'll go into the details of all these applications, because these are basically the all and metamaterial inspired concepts. And as I mentioned, that we have worked on compact wideband and ultra-wideband antennas. So printed CPW fed ultra-wideband slot antenna. This was for one application with Vikram Sarabhai Space Center. And this is a very fantastic design, which is basically a dielectric antenna along with concept. It's a hybrid concept where you have a monopole, which is basically a vertical rod erected on the ground plane, which is basically a very classical antenna, as you know, the Hertzian dipole, Hertzian monopole. But this is a narrowband antenna. When you cover it with some dielectric material in the form of a cylindrical shell, you can tailor the geometry, you can tailor the epsilon r, you can tailor the monopole as well. So it gives a very wide band response. You can typically get more than 150% bandwidth for such antennas. But Our goal was not to basically just increase the bandwidth. Our goal was basically to reconfigure the bandwidth, control the bandwidth, so that we can use the same antenna for different kind of applications. We proposed a new technique where the antenna can be loaded with some kind of caps. So these are some metal caps which will be loaded on the antenna, which combinedly gives this particular configuration that we have a monopole, you have the dielectric, and there is a metal cap loading. Now, depending on the inner diameter of the metal cap, which is basically a metal ring you can think of, when it is loaded on that, depending on the dimension of the cap you are loading on that, you can actually control the bandwidth of the antenna. And the controlling factor is from almost 140% to 24% from the same antenna. And the beauty is the radiation pattern of the antenna remains invariant, even though we can control the bandwidth for different kind of applications. This is what I am going to discuss in a very detailed fashion today, that is metamaterial inspired antennas and circuits. So I'll be coming into details of that. These are some kind of basically filters, very novel notch filter with very high rejection and very high transition from passband to stop band, very high roll off you can say. And some of those applications have been used on antennas, like this is a Vivaldi antenna, as most of you might be knowing that this is under a family of tapered slot antenna, because the slot is tapered gradually and you get radiation of different frequencies from different areas of the antenna. So this is a fantastic ultra-wideband antenna with very high gain towards the axis of the slot. But this antenna, when is loaded with some kind of resonators, you invoke a different kind of antenna response. So this is I'll be discussing in very detailed fashion. And this concept have been further used by one of my PhD students who has just submitted the thesis a couple of days before. He has used this concept for a horn antenna, and that horn, when loaded with some kind of resonator, can give you the frequency notches. He is a scientist from National Remote Sensing Center, Hyderabad, and they have used these concepts, which was basically a raw physical concept back 2005-06 when I started my work in this particular area. But now that concept is very nicely used and exploited for rejecting the adjacent channel noise or interference from a ground station receiver. And further, this kind of concept have been extended in so many antennas, and this is a particular design which is basically called the balanced antipodal tapered slot antenna. So there are, you must be knowing about this geometry, where you have a microstrip on the other side which actually excites the slot, but there is some cost you have to pay in terms of feeding mechanism, etc. But if you can make an antipodal configuration where your metallization and the ground are on the opposite side of the substrate, you can start with a microstrip line feeding, then make a coplanar strip transition, and then come to the tapering of the slot. But further, this antenna is improvised by putting an additional ground layer on top, and thereby you make the structure as a balanced structure. So this is the overall structure. This is the intermediate sandwiched layer, which is represented by blue over here. And before screwing these particular two layers using some dielectric screws across these holes, as you can see probably, I just took a photograph in this way so that the intermediate layer can be made visible. These are nothing but some chalks which we use for teaching in Blackboard, which we are missing for last several months due to the pandemic. Anyway, so I'll be coming to detailed of design of all of these things, and some more concepts related to reducing the mutual coupling or enhancing the isolation for MIMO applications. This is something which I'll not be covering today. And this is what I was discussing in a little bit brief manner in the previous slide. This is the UWB balanced antipodal tapered slot antenna for low cross-polar radiation. In a nutshell, I can just speak very fast that this is the cross-sectional view of an antipodal Vivaldi antenna. You have metallization here and metallization on the ground plane. So these two metals are on the opposite side of the substrate. That's why you see it here and here. So this blue is top metal, and this chocolate is the bottom metal on the bottom side. But what happens is, for such configuration, your electric field is skewed, and this electric field skewedness is more predominant in this particular region, because here the separation between top and bottom metallization is less. So that skewed electric field produces an unwanted component of the field, which is responsible for cross-polar radiation. So if we want to kill this cross-polar radiation, we have to balance this electric field by producing another electric field which will be oppositely oriented with respect to this red one. But how do you do that? So it's a very simple idea. What we did was, as I mentioned already, that you put one more metallization layer on top. So this is the resultant structure. We call it balanced Vivaldi antenna, balanced antipodal Vivaldi antenna. So you have a ground layer here and you have a ground layer here. Now what happens is your electric field is skewed, still it is skewed, but it is like this and this. Now simple 10 plus 2 vector algebra you apply. So this field has two components, the green component and the red component. Red component is undesired, but this electric field is also have two components, one green component, another red component. So these two red components are now effectively cancelling each other, and thereby you enhance the cross-polar performance of the antenna, while the copolar component are additive. And this is even though that antipodal configuration is very popular, its cross-pole performance is not that great, especially at high frequency. As you can see, at high frequency, this component will be more significant compared to this component. But now with this improvised design, irrespective of the frequency, you have enhanced the performance of the antenna in terms of the cross-polar performance. Anyway, I'm skipping this particular slide because I'll be discussing this concept in a very detailed fashion, antennas for cognitive radio applications. These will be towards the end of my presentation. And same over here, I'll show this experimental demonstration, and in fact, I have some interesting video also that also I would like to show and explain the concepts. And as you can see, just in a nutshell, because I'll be coming in detailed fashion, by using a switch, a single antenna, and some kind of control mechanism with a microcontroller and a motor, we have shown that the antenna can be combinedly electronically as well as mechanically reconfigured for a multifunctional operation. So this is some experiment that we did, because I said electronic reconfiguration. So some pin diodes or some varactor diodes, etc. are involved. So this is just some kind of measurement setup for some filter application. And these are some expressions, some theoretical expressions, which I'll be explaining shortly. And as you can see from these two responses over here, this is the response of the same antenna for two different configurations. So this configuration shows that this is basically a narrowband antenna, which is providing a sharp resonant response at different frequencies depending on the type of switches which you will be actuating. And the same antenna for some other combination can give you the frequency notched ultra-wideband response. So these are the two concepts I am going to discuss in a detailed fashion. This is not exactly in sync with my today's talk, but I have talked on this topic in few occasions. Probably those who are interested, you can see in some YouTube, probably some of my lectures are there. Indo-Canadian Spark workshop was conducted by Dr. Toimur, where I talked on detailed topic on this one. Dielectric resonator based wireless power transfer and energy harvesting applications. So this is something which we have started recently. A couple of PhD students are working, not exactly on dielectric resonator based WPT, but overall on WPT, wireless power transfer. So this is just an experimental demonstration of short distance wireless power transfer using the split cavity resonator and the dielectric resonator. As you can see over here, this is the experimental setup. with split cavity resonator and dielectric resonator placed. And this work was published in Journal of Applied Physics in 2020. And this is something which we have started recently related to photoconductive antennas. Again, I am not going to in details of that on today's talk, because this is a little bit different ball game. Such antenna requires some kind of extra engineering apart from the antenna engineering, because these are printed on semiconductor substrate, and there are some optical technology to excite this kind of antennas, and you need to have expertise and facilities in nanoelectronics, photonics, antenna engineering, material science, etc. And as I said, that this is something which is futuristic, and we have printed rather fabricated this type of antennas with collaboration with Space Application Center Ahmedabad. This involves clean room facility, etc. It's a little bit very difficult for conducting this type of research for an academic institution until and unless you are having very high-end facility. And again, I'll try to talk on this topic later on in some other occasion. So this is some antenna we have designed with National Remote Sensing Center Hyderabad for satellite tracking applications. So probably I took a little bit more time than what I anticipated to give you a virtual journey of our research activities in our department, and also in collaboration with some of institutes and other organizations. So with this, let me go into the details of today's presentation. I'll spend a significant amount of time on introduction to metamaterials. Then I'll move to some part where there have been some pioneering work by few groups, metamaterial inspired small antennas. I'll talk a little bit of our work also on that particular area. And then I'll be moving to metamaterial inspired technique for gain enhancement, frequency notched ultra-wideband antenna, multifunctional ultra-wideband antenna, and then try to give you some ideas for future directions, etc. So this is a very well-known topic maybe now, because now we are not in the era of 2005 or 2006 where metamaterial was like a very, very hot cake, and it was considered as one of the breakthroughs in that particular decade in the area of electromagnetics. And as you know, Dr. Penji, Dr. Smith, Professor Kalos, Professor Ito, they are some of the founder figures in this particular area of metamaterial. But if you are a researcher in this particular area, you should know the chronology. And if you really see, then you'll see that Victor Veselago was a person who didn't do any experiment, neither any theoretical estimation, etc. But he first conceptualized this particular idea. Something is popping up on my screen. Sorry on that. I think because of some auto reminder kind of thing. Anyway, so there are two different school of thoughts on metamaterial. The first one was actually resonant particle metamaterial, RPM, which was by group of Smith in 2000. As you can see, there are two different kind of resonant particles. One is split ring resonator, and another is basically thin nanowires. And by making it as a basis, if you can form a lattice with that basis getting repeated, you can get a three-dimensional structure like this. And this, depending on the proper excitation orientation of the electric field and magnetic field, can invoke and can provide a phenomenon which is normally not available in nature. That's why it is called meta. The term meta means which is something which is not available in nature, beyond the nature. Okay, so experimentally and analytically, you can show that such material can give you a dispersive mu and epsilon, and over a certain frequency range, that mu and epsilon can go to negative. Another school of thought on this metamaterial is transmission line-based metamaterials, which are basically introducing some artificial inductors and capacitors in a transmission line in a complementary fashion, because you know from the equivalent circuit of a transmission line, normally you will have series inductor and shunt capacitor. But if you can make a meta transmission line where you want to introduce series capacitor and shunt inductor, you can get a complementary response, and there are a lot of applications. So these are the two different school of thoughts of metamaterial. Initially there was some clash also, and I'll be coming to that part very soon. But those who are going to start their research journey or research career in this particular area, please go through the details work from Professor Pendy, and you can probably read some of the material by Professor Bing Monk, Professor Ricardo Marcus, and other people. And as far as the applications are concerned, you will see plenty of papers in IEEE and other journals of late. And I can give you some resource material towards the end of the presentation. So this is a more of historical background and chronological development of this particular subject. So as I mentioned, that history dates back to 1968, where Victor Veselago first studied the effect of negative permittivity and permeability theoretically. And then we have pioneering work by Dr. Pendy, one on SRR, another with the thin nanowires, proposing the different kind of structure for producing artificially negative mu and negative epsilon. Then first experiment by Smith, and then 2005 onwards, some applications, especially in the microwave circuits, microwave passive components, design of miniaturized passive components like power divider, phase shifter, zero delay phase line, all these things started appearing in the literature. And antenna applications came a little bit late, but around 2010, maybe plus minus 1 year, some articles are available. And some of the applications are gain enhancement, some of the applications are polarization conversion. We have contributed in multifunctional design concepts of the antenna, radiator independent design of frequency notched antenna, and so on and so forth. Over the last few years, the metamaterial research has taken a new dimension. Now people are calling it intelligent surface of meta surface, where we are not going for volumetric material concepts, but we are having an additional layer on top of the antenna or on top of any structure, and thereby trying to change the polarization, trying to change the gain, trying to sometimes do beam scanning applications also. So this is some of the recent applications which are coming up. But those who are at the very beginning or at the initial stage of research work, please go through some part of theoretical work also, because you need to know what is a Drude-Lorentz model. And as you can see from this particular equation, that effective value of epsilon, which is given by epsilon naught into 1 minus omega c square by omega square. This suggests that if you operate below a cutoff frequency omega c, you can actually get effective negative value of epsilon. And effective negative value of epsilon is not completely uncommon. Those who have studied the dispersion, especially the anomalous dispersion in connection with Clausius-Mosset relation and Drude-Lorentz model, you must be familiar with this kind of concept. But what Professor Pendy did was something which was not available in literature. It was his thought that two oppositely oriented C-shaped metallic ring printed on a basic dielectric material, which might have an equivalent circuit like this, because it will induce current and oscillating current across the loop, and also the displacement current going from one loop to the another loop, right? And because they are printed on a dielectric substrate, they will form capacitance, which is a distributed capacitance, which can be calculated by techniques like coplanar strip line concepts. And there might be some loss, so L, C, and R are represented, and he calculated the resonance frequency for this type of structure and showed mathematically, please go through the classical paper, that the effective value of mu that he derived is something like this. So this is called a Lorentzian plot. around a frequency which is called the resonance frequency of the structure, these overshoots below the frequency and very much undershoots just above the frequency. And here you get a frequency range where you get a predominantly negative range of epsilon. So this is fundamental of double negative material. As I explained, you have to use two different clusters or two different unit cells. One is in the form of thin nanowires, and you can show by some EM simulation as well as by analytical technique that when you make an effective medium with thin nanowires with electric field oriented towards this nanowire, otherwise it will not work, because orientation and the polarization is very important for electromagnetic engineers. So when you make a medium like this and excite with the axial component of the electric field, such material gives you a negative value of epsilon below a frequency which is called the plasma frequency. On the other hand, when you have split ring resonators and they are oriented in a fashion such that you have excited them with an axial magnetic field. So magnetic field is perpendicular to the plane of these SRRs. So this is one type of split ring resonator I am talking about. There might be different other variants, in fact many other variants, but the fundamental operation remains same. So for such type of excitation, actually it's a, as you know that this is like a dipole type of structure, so this will give you electric resonance, and this is like a loop type of structure, so it is more like a magnetic dipole and it will give you a magnetic resonance kind of phenomenon. And for such structure you can extract and you can verify that effectively the medium provides a negative value of mu over a frequency. So this is a very simplified experiment I am talking about. In fact, you can do this experiment by producing this type of material and by measuring the S parameters, and using the S parameters you can actually later on extract the effective value of mu and epsilon by some standard techniques which are called the metamaterial extraction technique. So the fundamental papers is by NRW, that is the Nicholson, Ross and Wyatt technique, and then there have been quite a few modifications on that particular thing. And this is basically the last one, which is combination of these two. And when you have an axial electric field, I mean wire oriented electric field and axial magnetic field towards the loop, you can invoke the combined response and you can get the double negative nature. Now the question is, if we really have such material, we can engineer such material, then we need to think of applications, or it should be a purely physical concepts. So metamaterial, initially it was more of a scientific experiments, and but engineering applications are less. But now over last 10 years or so, a lot of engineering applications have come into picture. So in my talk, I'll be talking on different kinds of applications now. But before that, let us try to understand a little bit more on classification, because now if I assume that mu and epsilon can be both positive and negative, then we can have these 4 quadrants. So you call it forward wave propagation, or this is conventional material, you call it DPS, double positive material. And if you are in second or fourth quadrant, you have either epsilon negative or mu negative. So you call them ENG, epsilon negative, or MNG, mu negative material. And if you are over here, where you have both mu and epsilon negative, you can call it double negative material or left-handed metamaterial. Why they are called left-handed, I will be coming to soon. And this yellow layer, for which the epsilon is very small, it's very small, either positive or negative, you call them as this is mu is very small, either positive or negative, we call it mu near zero materials. Now this is another interesting source from Wikipedia and other places. You can see that is, as an optical engineer, if you assume that you can refractive index negative, then you will observe the reversal of Snell's law. So the light beam which is supposed to go in that direction, the angle theta becomes negative, and again when it is coming from negative refractive index material to positive refractive index material, you have a reversal of Snell's law. So initially people tried to understand metamaterial with this kind of basic physical interpretation and etc. Less of application. But now over last 10 to 12 years, a lot of new applications also has evolved. So as I talked that there are two classes of thought, the resonant particle metamaterial approach and the transmission line metamaterial approach. So these are the salient features of the two approaches. This consists of sub-wavelength resonators, narrow band structure, a large loss due to their resonance nature or Lorentzian nature. And this approach was highly criticized by the other group, which is the transmission line metamaterial based approach. And the second approach consists of sub-wavelength inductor and capacitor. And as I said, these inductors and capacitors are basically not the natural transmission line based inductors and capacitors. You have to create the structure, or you have to use them for some applications as the SMD components. And this can mitigate the narrowband problem of the resonant particle metamaterial approach. But Professor Ito showed that these two approaches are not significantly different. In fact, the resonant particle metamaterial approach can be derived from the transmission line metamaterial approach. So over next 3 to 4 minutes, I'll do a little bit of analysis for those who are at the beginning stage of their research journey in that particular direction. Probably this will help. So I just want to show that what do we mean by left-handed material and what exactly is the left-handed material from the very basic Helmholtz equation, which is derived from the Maxwell's equation. We want to understand the wave propagation in the left-handed media. So Helmholtz equation, as you know, is governed by this equation, and her n is the refractive index. So the beauty is this equation is invariant of the material because it is n square. So whether you have a negative refractive index or positive refractive index or mu and epsilon, which is positive or negative, this equation is not going to be changed. So as it involves squared refractive index n square, so this equation is not affected by such changes. Solution to above equation will remain unchanged after a simultaneous change of the sign of mu and epsilon. Now Maxwell's first order differential equation, as you know, the Faraday's law, curl E is equal to minus del V del T, which in the phasor form you can write is as j omega mu h, and curl H is equal to del D del T. You have ignored the conduction current, then you can get this form, which is j omega epsilon E in the phasor form. Now for a plane wave, how do you represent your electric and magnetic field? You represent it in this fashion, right? Now if you apply the Maxwell's first order differential equation, then you know the wave vector k, electric field E, and magnetic field H constitutes a relationship like this. And from that you define many things like intrinsic impedance, phase velocity, group velocity, etc. Now from this equation, you clearly understand that electric field, magnetic field, and the propagation vector k constitutes a right-handed triad. So E vector, H vector, if you take a cross, you get k in this direction. And that is also the direction of the pointing vector S. That means your energy, the wave energy, and the wave front moves in the same direction. So that's why we call it, it's a right-handed triplet, E, H, and K constituting a right-handed triplet. Now what happens if you imagine that the sign of mu and epsilon are simultaneously changed, and of course you have to have such material, but as a mathematician or as a pure physicist, if you think in that direction, then you have to rewrite this equation in this form, because you are saying your mu and epsilon both can be negative. Then you will write your first equation in this fashion, because of the negative value it will appear with a negative sign, so you better put a mod over here, and second equation also appears like this. Then what happens here now is you have the k vector oriented in the opposite direction, whereas the pointing vector, which is still the E cross H, is in this direction. That means the wave energy, that is the pointing vector, and the direction of propagation are now anti-parallel. So such a material is called left-handed material, and this constitutes a left-handed triplet. So the outline is E, H, and K forms a left-handed triplet. Another dimension to this work you can understand from here as well. If you know the time averaged energy density, as you know, the energy has two components, the electric energy density and magnetic energy density, which is replaced by half D dot E and half B dot H respectively. and considering the phasor variation, and D equal to epsilon E and B equal to mu H for linear dielectric and linear magnetic material, you can write the non-dispersive energy density in this fashion. So this equation is applicable for certain cases, of course, but if we have epsilon and mu negative, both the material parameters are negative, then this equation will lead to something which is unrealistic or non-physical, because it will end up with a negative energy density. So this equation holds good only for weakly dispersive medium. If you have a fully dispersive medium, and then you have to rewrite this equation in this fashion, and where this equation is basically a special case of this equation, where you have epsilon and mu as constant, not a tensor or fully dispersive, then this equation will be leading like to this equation. Otherwise, if you really want to make it more general, where the equation should be applicable for any type of material, you have to rely on this more fundamental equation, and this energy density for quasi monochromatic wave packet is governed by this equation. Now, look at these two terms, del omega of omega epsilon and del omega of omega mu, which are compatible. This should, because energy density has to be positive, and each of the electric and magnetic energy density has to be positive. So this must be 0 and this also must be 0. So if you want to comply these two equations, along with the fact that you have mu and epsilon negative, then you have to satisfy these two conditions, that is del mu del omega greater than equal to mu by omega. It is just one line derivation you do, please later on and check, and then these two conditions you have to satisfy. Now, what is the outcome of this? Why I am spending that much of time in explaining all these things? Because from this expression, that differentiating the wave vector k square, you can write del omega of k square in this fashion, and as you know, by providing a omega at the denominator and numerator, you can write it as in terms of the phase and groove velocity. So our Vp is basically omega by k, and Vg is equal to d omega dk. So now, why I did that? Because we know that k is also related with mu and epsilon in terms of the frequency. So if you take a derivative of this with respect to omega, you get this particular term. Now, what did we understand from previous slide? That for physical condition, this term and this term must be greater than 0 for mu and epsilon less than 0. So what we see is this term del k square del omega is less than 0 for a real double negative metamaterial medium, because this is positive, but you have mu and epsilon negative. So you have this term negative less than 0. That means this equation from 1 and 2, you can tell that Vp times Vg is less than 0. Vp and Vg are phase velocity and groove velocity respectively. As you know, the groove velocity indicates the overall velocity or the velocity with which the wave energy travels, and the phase velocity is the velocity with which the phase moves. So it implies that the wave packets and wave fronts travel in opposite directions can be considered as an additional proof of backward wave radiation. So I spent probably 5 to 7 minutes in explaining the things from the very fundamental physics, but this is a more interesting way to understand this particular concept. So you see, let me assume that I have 3 layers of medium. The first layer and third layer are conventional material with mu and epsilon greater than 0, and the intermediate medium is an engineered medium. So I can play with that intermediate medium. I can have mu and epsilon both positive, both negative, one of them positive. So I have basically 4 combinations for the intermediate medium. Now I want to see the wave propagation. If I launch signal here, and I want to see what is the response I am receiving over here for all those 4 combinations. So that is the intermediate medium, positive, 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 negative, negative, positive, and negative, negative. So first quadrant is indicating that both the parameters mu and epsilon are positive. Now you see, for such a medium, when I'm launching the signal from here, I see the full signal is received. So as you can see, the phase and the energy are traveling in the same direction, because that's what we expect, because mu and epsilon both are positive. Now, if one of the terms are positive, either mu or epsilon, then basically your propagation constant becomes purely imaginary. So in such case, you are not supposed to get energy over here, because this medium will not allow the energy to propagate through. So let us see what happens. We have launched a signal from here, and I see that it is effectively either absorbed or reflected. Something is happening, but I don't see much response over here. And same thing happens for the other case also, where you have epsilon negative and mu positive. You see there is effectively no wave reaching to the third medium. What is the application? So probably this type of medium will not allow the signal to pass through. Then we have to see whether it is reflecting or it is absorbing. If it is absorbing, we can think it is for some absorbing applications. Otherwise, what are else applications that can be derived? That is what the different groups have contributed over last few years. And this is the fourth case, as I mentioned, when you have both mu and epsilon negative. As you can see, I will play it once more. You can clearly see that in the intermediate region, the phase is moving in the opposite direction. So this is a very simple simulation, of course very idealistic, because we have not considered dispersive nature over here. We have not considered the loss. We have not considered how these mediums are generated. But as a theoretical person, if you assume that you have 4 combinations of engineered medium, then this is what you are expecting. So this is the first part, which is mainly the physics thing. Now I'll be coming to some of the applications. So as I mentioned, the split ring resonators is one of the integral component for the metamaterial research. So I spent some time on these SRR structures. So I have already explained that you have 2 C-shaped SRRs, that is the conventional structure, 2 C-shaped, basically the rings which are printed on a dielectric material, and it has all the dimensions given over here. And then this is called circular structure, but you can have square structure or hexagonal structure. So these are the 3 combinations which we have used very extensively in different part of our work. And I mean, one of the important parameter that is to understand the estimation of the resonance frequency very accurately. So when we started work, like this was the most fundamental paper that we are following for calculation of resonance frequency of split ring resonator. Whatever application you do, whether you are thinking for polarizer or absorber or antenna applications, frequency notched antenna applications or multifunctional antenna design applications, calculation of the resonance frequency of the SRR is very, very important. So here, when we were doing this experiment, we got a lot of deviation between the theoretical results and measured results. So that was a striking point. We proposed a modified equivalent circuit, and this circuit was first published in 2011, and later on we have shown it in IEEE transactions for antennas and propagation as well. Anyway, so I have skipped a lot of things. For that you have to see the journal papers that I was showing, but nevertheless the closed form expressions for these 3 resonators, the square one, the circular one, and the hexagonal one, are like this. So it involves calculation of the inductance and calculation of the capacitance, which is basically the distributed capacitance between these 2 rings. And that's why you have the C pool per unit length capacitance, and this is R average, which is the average dimension, and it involves some gap capacitance which is formed over here as well as here. And the other expressions are almost identical, but depending on the dimension, your the capacitance as well as the inductance will change. So this LT is the total inductance, equivalent inductance of the structure, And but we proposed a very simplified but yet very effective and accurate equation for quick estimation of the resonance frequency of such resonators. So I will give an example, because we have got so many emails across the globe for last 10 years regarding that accurate estimation of the resonance frequency of split-ring resonators. So then, in one of our articles, which was published in IEEE Transaction on Antennas and Propagation, we provided one specific calculation in the appendix of the paper. So those who are interested can please follow this article, March 2018 IEEE tab. And for a given SRR dimension printed on a given dielectric laminate for a provide given thickness of the substrate as well, we have shown all the steps and calculated the resonance frequency of the SRR. And you can follow all the steps one by one. And for that application, it was basically one application related to antipodal tapered slot antenna. So there it was for 4.2 gigahertz application. So you can basically verify these concepts. Now these SRRs, we have shown applications into the different areas. It is for different kind of filters, the notch filter, multifunctional antenna, gain enhancement, and the simultaneous operation of the antenna for wideband, narrowband, and notched application. And as I mentioned at the very beginning, for some frequency notch technique for reducing the clutter, noise, and interference from the on antennas also. So this is one of the fabricated prototype I am showing here. As you can see, we have a realized prototype. Multiple split-ring resonators are printed on a dielectric substrate on the backside of CPW basically. And the idea is basically these sub-wavelength resonators, they are sub-wavelength resonators because their resonance frequency is much smaller compared to their dimension. And by loading them by different numbers, different dimension, even different orientation, you can tailor the resonance frequency. And this is an application towards the frequency notch filter. And when you design such circuit, you can actually show not only by EM simulation, but also by circuit simulation regarding their performance. So this is a equivalent circuit of what I showed in the previous slide. You have the CPW line, and you are terminating the CPW line by 50 ohm impedance. But as you know, because of the symmetry in the structure, actually, I'll just take a minute to explain something. So because of the symmetry, actually you can actually take half of this for your equivalent circuit representation, and other half will be identical, right? So if you take these half and then you have a 50 ohm termination over here, so you can think that you have this is ground plane, right? And this is also ground plane. So you can see from the boundary condition that these half and these half are actually parallel to each other. So because of that concepts, we have drawn the equivalent circuit of one of the halves. So thereby you can write it as 100 ohm, not 50 ohm. So it is 2R0, and this is also 2R0. And these equivalent circuit for different part of the transmission line, inductors and capacitors. And this is the equivalent circuit of your split-ring resonators, which are of different dimension. So this is for SRR1 and this is for SRR2. And as I mentioned that there are some orientations, different orientations, theta equal to 60 degree and theta equal to 90 degree for those two cases. So I can tell you about this one. Here we have intentionally used a different orientation. I'll explain that concepts very soon. So this is a realized prototype notch filter, and you can see some of the measured response over here, especially the last one, this one. And you can see by loading some resonators of different dimension and different angular orientation. Look at the roll off from passband to sharp notch band or the stop band transition. So with this kind of technique, you get a very sharp frequency response, and again from stop band to pass band response. This is something which is very great about this particular structure. Now, this is some passive component application. Now, the next part I am going to talk about is a little bit on metamaterial inspired antennas for electrically small antenna application. So, what is a metamaterial inspired antenna? First of all, it is an antenna which will be having sub-wavelength phenomenon. Sub-wavelength phenomenon means, as you know, the resonant antennas are always λ/2 or λ/4 if you consider the monopolar concept. But here you can do a miniaturization in the form of λ/5 to λ/10 or sometimes even better. Now, for such antenna, designing electrically small antenna is always very challenging because you know there will be a lot of capacitance associated with that, and you have to do the conjugate matching, which is not that easy. So Zilkowski was one of the pioneers in this particular area. He first reported electrically small antennas using the metamaterial concepts with very high efficiency, and then it can overcome the Chu limit, and also it can be reconfigured for various applications. So this is the fundamental definition of your small antennas. This is the Wheeler's definition. As you can see, this is called the radian sphere. If you can embed your antenna inside a sphere of radius a such that Ka less than equal to 1 where K equal to 2 pi by lambda, then you can call, if you satisfy this condition that Ka less than equal to 1, then you can call your antenna as a electrically small antenna, and Ka equal to 1 is actually the boundary, so you should have Ka less than equal to 1, and this was called a limit which is named as the Chu limit. I'll come to that Chu limit condition now. And the Professor Stiepest mentioned that for antennas which is having the PEC ground plane, for example, the monopole, if you have a ground plane over here, then this definition should be further modified. The modified equation for such antennas, as Professor Best suggested, should be Ka less than equals to 0.5. Now, as I mentioned, that electrically small antenna design is always a challenge because of what you all know: low radiation resistance, low radiation efficiency, huge requirement for matching, and the matching network is not that easy to realize, and it involves many other limitations. That is, you cannot beat the Chu limit, etc. So this is the fundamental limitations of small antenna. As an example, we propose it over here. If you have a small dipole, that, as you know, that it will give you capacitive reactance. So if you want to really make your small dipole antenna properly resonant and to have a good matching, you have to get rid of that capacitive reactance. So for that, what you can do is you can put a small dipole inductively over with inductive matching kind of thing, and overall your antenna looks like this. You have the antenna, you have because it is small, having capacitive reactance, you put an inductor, and then you have to do further λ/4 resistance transformation, and then you can excite your antenna through a source. So this is the traditional concept of electrically small antenna. All antenna designers, whenever designing electrically small antennas, faces this particular problem. The proposal by Professor Zilkowski was something like this. You get rid of this kind of arrangement. You can try to think of embedding your antenna inside a metamaterial shell. He proposed one ENG shell, epsilon negative shell, which will produce effective inductance, and thereby, and the thickness of the shell will be used for matching. So by embedding the antenna inside such a shell, which was in his initial work was completely theoretical, no experiment. So that's what he proposed, and he showed that such an antenna can be an alternative, and it can solve the many of the challenges that electrically small antenna design involves. And then these are fundamental limitations of small antennas, as I mentioned: quality factor, bandwidth, radiation efficiency. And then when you talk about quality factor, normally we use it for circuit, and you all know that quality factor for a resonant circuit is defined like this. But for an antenna, this definition has to be thought in a different fashion, because for a circuit, we want more energy to be stored, we want less amount of power to be lost in terms of radiation. But here we want more in the denominator for an antenna. So depending on the situation, you will define either of these two, and this loss can be not only the radiation loss, it can be conduction loss, it can be dielectric loss, it can be surface wave loss, etc., etc. So, but as an antenna engineer, we want more loss due to the period, not any other loss. We don't want power loss by conduction loss or dielectric loss or surface wave loss. So if you incorporate all those concepts, then you will see a fractional quality factor also coming into picture. So considering those fractional quality factor and the radiation quality factor, you can define your equivalent or total quality factor in this fashion. So this is again a bit fundamental, but as an antenna engineer, we should know this. And this is what Professor Chu predicted long back, and he mentioned that what is I mean, just going back over here. So we want actually to reduce the quality factor for an antenna because we want more in the denominator, because we want the power to be lost by radiation. So Professor Chu predicted that you cannot beat this particular expression for the quality factor of the antenna. That means you cannot design an antenna whose quality factor will be lower than this. But there was some error in the Chu's equation. So Maclean actually corrected that one, and he proposed a new formula for the Q value for that antennas, and he called it Q exact. And so this is the error that you get from the Q exact and Q Chu. And for K less than equals to very less than 1, these two are almost same, but there is a significant amount of deviation towards the high value of K. So this is more of a corrected result. Not only that, he proposed another formula for antennas which are circularly polarized. So this is some work that one of my students, he is doing PhD now, and we collaborated with Professor Iyer of University of Alberta while doing this particular work. So this is the radiation enhancement by metamaterial shell. So this is basically it can be a ELS or MLS. It is surrounded, and it is very small, electrically small. So it is surrounded by a material which, as you can see, region 1 is free space, region 3 is also free space, region 2 is a dielectric, and I mean it's a, you can say it's a tensorial material with mu and epsilon. You can have different kind of frequency dependent nature, and we come to closed form expressions after very lengthy procedure and calculation analytical technique, and we defined something which is called PR, which is called the power ratio, which is basically the amount of power radiated by the antenna without this metamaterial shell and with this metamaterial shell. And as you can see, the plot of PR, due to the enhancement of the power and due to a better matching, thanks to this resonance condition that you have to achieve, you see the PR is close to 8 dB at some value. That means the antenna with this loading of metamaterial shell is doing much more effective radiation. So I'm not going into the details of the work. You can please follow this article, and if you have confusion, always feel free to interact with me. And this is another piece of work which is related to gain enhancement or radiation enhancement using the metasurface lens. This we have reported recently in a journal. That initial work was presented in a conference. I think it was in Bangalore in 2017, which is basically a metamaterial lens which is loaded on top of an antenna, which is basically a planar fed dielectric antenna, and the matching is not the point. The point is basically the gain enhancement of the antenna due to such loading. Now I come to the last part of my talk, where I'll be mainly talking on planar antenna applications of metamaterial, and this is like introduction inside the main talk. So here what I want to show is that how we have evolved the ultra-wideband antenna and how we have used the ultra-wideband antenna for multifunctional applications. So this slide I have used in many other talks, so it might be very common to quite a few of you. So the main point that I wanted to mention over here is the percentage bandwidth. You can see this particular equation, and you can understand that 200% is the absolute limit, and that absolute limit is not just touchable. So you can design an antenna which bandwidth will be close to 200%, but it will never cross that, because from this expression FL equal to 0 gives you that absolute maximum value, and FL0 is not possible because DC can't be radiated, right? So and this is the evolution or journey on different families of antennas. And in this lower part of the slide, the point that I want to show you is how we have designed some antennas which can actually use these idle holes, the spectrum holes or the white space in a dynamic fashion, which is required for modern cognitive radio application. So this is the main focus of the last part of the talk. And such an approach is basically towards a goal, and the goal is better utilization of the spectrum. Spectrum efficiency will be enhanced if we can have a mechanism by which we can use the idle slot of the spectrum. When primary users are not using the spectrum, we can use the spectrum. So this animation towards the end is actually sharing the story that I am going to show now. These are like primary users, and as you know, the primary users, even though they have the perpetual license to use the spectrum, sometimes they are idle. So when those primary users are idle, we should use those spectrums, rather they should relinquish the spectrum to the secondary users, and thereby you enhance the spectrum efficiency. So this is the whole story. And as you know, that many of the upcoming concepts, starting from smart city to smart village, digital India, and IoT applications, wireless sensor area network research, there would be many applications where we need to have smart system that requires multifunctional antennas, where the antenna should be capable of identifying the spectrum holes, at the same time communicating over the spectrum holes. So this is what I am going to discuss over next 20 to 25 minutes, and then we get a break. I keep some sufficient time for interaction. So this is the ultra-wideband. I will not take time on this, because this is mostly, most of you must be knowing that in 2002, the FCC identified, or rather recommended, this particular band for ultra-wideband communication, but at the same time, due to the existing users present over the band, it provided, or it restricted a spectrum mask. So this spectrum mask, that means your power level for indoor and outdoor application should follow so and so values, has to be always obeyed. And this is called the same power level, but it is in terms of the absolute value, that is the power spectral density. So you can have the whole ultra-wideband you can use, but you have to obey these spectral masks. So that is the main point. So once this FCC provided this spectrum for ultra-wideband applications, the antenna engineers started antennas for such frequency band. And these are some of the antennas you must be knowing: spiral antenna, printed monopole antenna, notched or tapered slot antenna, as I discussed. And then you have antipodal tapered slot antenna, the one I was mentioning earlier. So they have different kind of characteristics. Like you have to see, when you say it is ultra-wideband, you have to see not only the frequency band response, time domain response also you have to see. Now I start my journey towards the ultimate goal of designing the multifunctional antenna for some of the modern smart radio applications, which involves the cognitive radio, software-defined radio, etc. So this is the frequency band of UWB, and as you know, within this UWB band there are some narrow bands. So we cannot design an antenna which will be radiating over the entire frequency with all over the entire band. But what we need are antennas which won't be radiating at certain frequencies, because the WiMAX, WLAN, and other narrowband services are coexisting. So I'll be coming to the solution. I just mentioned the requirement. And then if you talk about a multifunctional antenna, then it has a very close relationship with reconfigurable antenna. So reconfigurable antenna, as you know, can be of frequency, pattern, polarization, or combined reconfiguration, and you rely either of the electrical, physical, optical, or material change based technology to design a reconfigurable antenna. But the focus is on the feature, whether I want to change the frequency or the pattern or the polarization, thereby you call it a reconfigurable antenna. As I mentioned, it is very much linked, but multifunctional antenna, the focus is not on feature, but on application. What I said a few minutes before, that we want to have a solution where we can use these spectrum holes and we can provide the spectrum holes to the secondary users when primary users are idle. So such an antenna which can do the frequency scanning, spectrum sensing, as well as communicating together can be called a multifunctional antenna. And this is what Professor Christodoulou has spent a lot of time on this particular research. And his proposal was something like this. This is a dielectric substrate. On this dielectric substrate, you have an antenna which will be doing the scanning for locating or searching the spectrum. And there will be multiple antennas which are for communicating. And this particular part, one of his experiment, he has shown by putting this particular part as a mechanical reconfiguration, you can excite one of the antennas at a time because this is a rotatable section, and thereby you can take care of both the functionalities. So these antenna will be doing the sensing, and these antennas will be doing the communicating, antenna 1, 2, 3, and then etc. But we wanted to have a smarter solution where a single antenna can do both the scanning as well as the communication. Okay, so little bit of more of these concepts is basically the, as I was talking about, that cognitive radio concepts. So idea, as already mentioned, when primary users are idle, we should relinquish this white space to the secondary user. So SU at secondary user over here, and this is one of the situation which is called spectrum interweave situation. And another situation is you can have primary users, but still you can give not only the primary user's frequency, you can provide, not only the idle frequency, but also the primary user's frequency to the secondary users, provided they use a proper polarization, they use a proper spectral mask, that is their allowed interference level is this much. So with these two conditions, you can give more bandwidth to the secondary users. So such a radio which has the intelligent capability of identifying the spectrum and then using those idle spectrum for the secondary users is called cognitive radio. That term cognitive means something which is intelligent and which becomes more intelligent by gathering information from the environment, etc. So cognitive radio front end is interweave scenario and underlay scenario. So we have wideband sensing and narrowband sensing or wideband sensing. So this is a common requirement. Now I have deviated a little bit because this part of the lecture is not related to metamaterials, but now I'll show how the metamaterial concepts have been used in designing antennas with this kind of features. So what I mentioned in a nutshell was from this article, Professor Christodoulou and his group. So you have an antenna which will be doing the sensing, that is the spectrum sensing, and you have an antenna which is for reconfigurable antenna which will be doing the communication at different frequencies. So now we'll try to see how such multifunctional antenna, frequency neutral wideband antenna, etc. that I mentioned can be developed using our concept. So next 15 to 20 minutes, I'm going to completely discuss on some of our own design and contribution in this particular field. Just a minute. So as you can see, this is a antenna which is coplanar waveguide fed. Most of you are aware of the geometry, and this is the monopole. But the main point that you need to see is these two guys sitting over here, which are basically sitting on the back side. These are the resonators, the split-ring resonators placed on the other side of the substrate, and the detailed dimension is given over here. So without these two resonators, this antenna is an ultra-wideband antenna. But with this resonator, thanks to high magnetic resonance of the split-ring resonator and coupling of the magnetic field from the CPW lines to the split-ring resonator, you basically create a frequency which will not be propagated, which will not be supported by this feed region. So this is a notch filter. So this notch filter and this antenna together is providing a frequency notched ultra-wideband response. So there are many other solutions. Why I am talking about this solution? Because this solution, the main idea is the notching solution is kept over here, whereas the antenna is kept over here. So the design of the antenna and the design of the resonator, which creates the frequency notch, are completely independent. Moreover, you can put any kind of radiator there and you can get that function. It need not be a circular monopole, it can be anything. It can be even tapered slot antenna, as I mentioned earlier. So this is the main advantage, and this notch is easily frequency scalable. You can redesign it as per your requirement, etc. And this is a fabricated prototype of the antenna I was talking about. So you can see this is the CPW fed monopole, this is the SRR, and some calculation is involved. You can quickly go through the articles. This is what the capacitance calculation, and this is the inductance, and you can get the thing. This is the results as far as the measured and simulated matching is concerned. S11 without SRR, as you can see, it is a good match over the entire band, whereas when you put the resonators, you won't get good matching, because that's what the resonator does. It doesn't allow the frequency at that frequency to be propagated. We did not use the metamaterial concept over here in explaining, but as a metamaterial engineer, you can tell that at a certain frequency, depending on the resonance frequency of this SRR, the medium doesn't allow that signal to pass through, and thereby that particular frequency, which is 6.34 gigahertz here, is a notched band. But I personally and our group personally doesn't want to use the term metamaterial here, because it is just one pair of resonators. When we have a bulk material, then only we should use the term metamaterial. So we use this as a metamaterial inspired antenna. We never said that this is a metamaterial antenna. There are a lot of mistakes, a lot of gross mistakes in many published articles. So when we do a research, you should be very careful on this kind of thing. Anyway, this shows the surface current distribution of the antenna at 3 frequencies. Intentionally, we have chosen the notch frequency and other frequencies. At other frequencies, antenna is excited because the resonator is transparent, whereas at notch frequency, the antenna is not excited thanks to the resonator's performance. So this is the measured radiation pattern of the antenna at E plane and H plane. This is E and H plane. That is repeated at different frequencies, 3.1, 6, and 10 gigahertz. And this is the extension of the work for reconfiguration for multiple notches. As you can see, when you have 2 pair of splitting resonators, you can actually create multiple notches because they are differently dimensioned. Because they are differently dimensioned, you will get a frequency 1 and frequency 2 from here. This one will give you low frequency and this one will give you high frequency. And those 2 frequencies can be kept closer to make a wider notch, or they can be kept isolated to make it a dual notch. So this is the article, compact dual SRR loaded antenna for dual frequency and wideband notch characteristics. So this is the fabricated prototype of the antenna with this particular concept. So till this point, I have talked about the frequency notching concepts, but this is what is the game changer. The game changer is following. You have a planar ultra-wideband circular monopole antenna. You have the resonators loaded. You get frequency notched ultra-wideband antenna, fine. But if you put a pair of nanowires, thin nanowires over here, which should be on and off. That means you should not make a fixed arrangement but you should have a mechanism by which you can turn on and turn off those wires, that means by switching arrangement. Anyway, if you have that, then you get a narrowband antenna response excited from the same antenna. So when you have SRR plus shunt wire loaded over here, probably you can follow this particular area in the fab, then you get a narrowband response. Why? Because these SRR and these thin nanowires together constitutes a band pass filter with very narrow pass band frequency. Earlier it was a notch filter. Now that notch filter, due to the inductance of these thin nanowires, is converted to a band pass filter, and thereby you get a narrowband response out of that. Not only that, if you can close this gap by some switching arrangement, then this becomes a CRR, closed ring resonator. And for closed ring resonator, you can follow this diagram. When it is a closed ring resonator, you again get back the ultra-wideband response, because the resonance frequency of such closed ring resonator doesn't fall within the ultra-wideband. And this particular idea, where a single antenna, as you can follow, the single antenna invoke multiple antenna responses, can be very, very useful for something which I discussed earlier, where you have the sensing antenna and reconfigurable antenna for communication. But till now, the antenna I have discussed in the last slide was basically two modes. One is notched ultra-wideband, another is the narrowband. But the cognitive radio concepts requires this narrowband to be tunable. That means I should have a mechanism by which I can take the antenna response, the matching at different frequency. Then it becomes a very, very useful candidate for the cognitive radio applications that I was talking about. Just give me a few seconds. Yeah. So if you want to do that, basically what you have to do is you have to have a mechanism by which you can take this matching frequency, you can make it reconfigurable. So this is an arrangement where we have done this reconfiguration, and this arrangement is very simple. It is basically in this particular paper, what we did was we changed the dimension of the resonators, and by changing the dimension of the resonator, as you can see, it goes from almost 5 gigahertz to more than 8 gigahertz. So this is a frequency tuning, and these two operations together can give a very good design for the multifunctional antenna I am targeting. And this is showing the complementary gain response of the antenna. In the blue one is showing the antenna gain for the notched antenna, where the gain falls at this particular frequency, whereas the black one is the complementary response. The antenna gain is good only at the narrowband frequency, and in the other region the gain is pretty less. That's what we expect from such an antenna. And now the dual complementary antenna, because it is a dual complementary antenna, because it can give you the notching, you can give you the narrowband response, etc. So you can verify the performance in terms of group delay. And for the two cases, as you can see, this is the configuration B and this is configuration C. So in this configuration, the group delay is high at the notch frequency. Configuration C is a completely wideband antenna, so you don't have any hump or anything over the broadband, which is 2 to 11 gigahertz. This I'll be explaining in a better way after a few slides maybe. But just to tell you, this is another way to interpret the results. This is the frequency and this is the distance from the fit point. And this rectangular contour plot, this is actually indicating the magnitude of the pointing vector. So in the first case, which is a notched response, you can see the pointing vector. This is actually the final feed end where the power is coupled to the antenna. So this is red, blue, and red. So that means only this particular frequency is not reached to the antenna, which is the notch band. In the second case, it is complementary. It is blue, red, and blue. That means only this filtered energy, this is the frequency now. So only this particular filtered energy will be reaching to the antenna. So this is basically the distance measured from the feed end. So if I just draw my antenna, it is basically, this is the CPW configuration. So this is what I am plotting. This is my distance 0, and I am plotting the pointing vector from this point to this point. So in that one case, I see only this particular frequency is reaching to the antenna. So that is the narrowband case. And in other case, only the entire spectrum excepting this particular frequency is reaching to the antenna. So this is another way to understand the result. So this is the uniqueness of the present design concept. This is applied for many antennas. As you can see over here, it is applied for some kind of Vivaldi antenna. It is used for even for horn antenna, as I mentioned, for some modified Vivaldi antenna we have shown. And we have used these concepts in designing some antipodal antenna with 2 different configurations. In configuration 1, we have the resonator over here. In configuration 2, we have the resonator over here. And the beauty is the notches are very, very sharp, very sharp. In no other technique, you will get such sharp response, both for configuration 1 and configuration 2. So this is the last part. Probably I'll take another 10 minutes or so, and I'll come to the closure. So this is what I am showing step by step. You all know by this time that this is a ultra-wideband antenna. I load it with some kind of resonator. It becomes a triple notched ultra-wideband antenna. And calculation is based on the theoretical estimation, which I have discussed earlier. And as I mentioned earlier, we have used the rotational orientation to change the resonance frequency in addition to the normal concepts. Please see over here, you are going to see some changes in this particular region. This configuration, as you know, is a frequency notched ultra-wideband response. As I mentioned earlier, if I have a switch here and here, and if I can turn on and turn off those switches, then the response will change. So I have connected a pair of switches there. Earlier it was a frequency notched antenna. Now with these 2 switches getting on, this is a narrowband antenna. Now I have an external mechanism. I can turn on and turn off my switch. So please have your concentration here. Then only you will be able, because it is a virtual screen. So you have designed an antenna which is working as a frequency notched as well as narrowband antenna. And these are the configurations. We did initial experiment at our facility at IIST. We just used a static switch, which is basically copper strip, loaded and unloaded. You can, it's like a sellotape. You can keep it to make it a closed switch configuration. You can just take it off to make it a open switch configuration. And 3 pair of resonators with theta 0, 60 and 90 orientations are loaded on the back side. And as there are 3 pair of SRRs, we need 3 pair of switches also. And those switches can be turned on and turned off to ensure the multiple narrowband configuration. So here I have skipped some of those animations. Actually, these 2 pair of switches at a time, one of them has to be actuated. Anyway, and triple notched configuration simulated current distribution. Earlier I talked about the pointing vector. It is same thing here. Now you can probably follow it in a better way because it is synced with the dimension. So this is the frequency and this is the distance. As you can see, the antenna part is truncated here. This is the full picture and this is the full antenna will be like this, right? So what you see here, due to the presence of these 3 pair of resonators, there are 3 frequency notches created. As I said, this color distribution is indicating the pointing vector. So M1, M2, M3, which are 12.8, 19.8, sorry, 7.65, 6.2, and 4.85 gigahertz. At these frequencies, the notches are created. Why? Because of these resonators. The highest frequency notch is created by the smaller resonators. Intermediate one is by the mid-sized resonators, and the low frequency one is the large-sized resonators. You can see the surface current distribution on the antenna on the first, second, and third notch frequency. You see the antenna is not excited at those frequencies. That is expected. And for narrowband configuration, it is much more interesting because for narrowband 1, narrowband 2, and narrowband 3, you see only a filtered power has reached to the antenna. You can see probably my pointer. Just wait a minute. You can see my pointer probably. here, here and here, we have this one. Sorry. Yeah. So you can check that narrowband 1, narrowband 2, and narrowband 3, which are contributed by those pair of switches and the resonators respectively. Now coming to the another important extension of this work is when we are loading these resonators and the switches along the feed line, the effective feed length of the antenna becomes a little bit on the larger side. So without going for such a longitudinal extension, what we did was we placed another pair of resonators on the other side. Like we have the substrate. On the back side of the substrate, we have resonators. We placed a superstrate on top of that. And on the superstrate, we placed another sized resonators, which are smaller. So these two guys will give one frequency, and these two guys will give another frequency. And then you have the switch as an intermediate arrangement. You can turn on and turn off the switches. And thereby, you can invoke multiple antenna responses from a single antenna by combinatorial loading of those superstrate and the switches and ensuring a mechanism to turn on and turn off the switches. So this is the equivalent circuit simulation, as I was telling earlier also. So because of the symmetry, you will take half of that. So it will be 2R0. And these are the equivalent circuit for the transmission line. And sometimes switch is on and off. So when switch is on, switch will be mimicked by this 2LP. It's an inductor. And there are other parasitics involved. And then you have a SRR on top, another SRR on bottom. So they are coupled, right? Magnetically coupled. So coupling coefficient are K1 and K2. Okay. So that's how you can make an equivalent circuit. And finally, what is the load? Load is an antenna, which is having an impedance, which is function of frequency. So you define that load as ZAF. The term 2 is appearing because we are producing the equivalent circuit of 50%. Other 50% is there in parallel with this. So if you consider that 2R0 parallel to R0 will give you R0, 2ZA parallel to ZA will give you ZA. So no point to get confused with this idea. You can follow, even if you are a beginner, you can follow this idea and you can do some significant amount of work in this particular direction. Okay. Now, I was talking about different kind of switching arrangement, etc. But I never showed any switch. I was showing only the copper switches. But practically, such a copper switch related work will not work because you have to make sure the switch is on and off, and you have a mechanism to do that. So this hello? Hello?
Yes, sir, you can continue. I think by mistake someone has. Okay.
Can you hear me?
Yes, sir.
Yeah. So this is an arrangement where we have loaded a pair of pin diodes, and as you can see, these pin diodes are loaded between the signal line and the ground plane. Another pair of SRRs are there on the back side, and you have these diodes over here, and you have a mechanism to turn on and turn off these diodes. So practically, a biasing arrangement is needed. You need to provide the DC for the diode to turn on. So this is the DC and this is the RF. RF will be connected to the antenna, and DC is only for the diodes. So you have a bias T for the experimental purpose. And as you can see, for diode on and diode off condition, the antenna response is completely complementary. The blue one is indicating the narrowband response, and the black one is indicating the frequency notched response. And the gain profile is also supporting that. And this experiment we did with Professor Frandhofer at Queen's University, who is a collaborator of ours, and Professor IIST. And you can see that interesting video. I hope it will run. You can see the arrangement that I am showing. Something has popped up. Not concentrate on that. Yeah, so you can see that now it is notch response, and now it is narrowband response. So there are some harmonics, of course, that you have to reduce by some mechanism. So from the same antenna, you can invoke multiple antenna responses, and as I showed through the captured video in a real-time experiment, you can actually design a multifunctional antenna. And these are the experimental stuff, and these are the diodes actually loaded. And these were the first experiment, and this was, a breakthrough, because this is the first kind of its antenna, where a single antenna give you multiple antenna functionalities. So just a second, sorry, yeah. So this is a reconfigurable printed monopole antenna. Before we did that experiment, next time we first verified these concepts with a CPW based planar filter, and as you can see, for two different cases of that antenna, the experiment is showing on only the filter part, but later on we use this concept on the antenna. You have S11, which is having two different kinds. One is the notched response, another is the narrowband response. And the gain also in a similar fashion. For the narrowband, the gain is appreciable only for a smaller range of frequency where you are interested. So this design concept is further extended for a frequency agile antenna, where you have the SRRs, and those SRRs are mechanically moved by a motorized rotation. This is a work which is an extension of our concept, but this work was, the primary worker was one of my BTech student. So these are the resonators which are movable thanks to a motorized rotation, which was actuated through an Arduino microcontroller. As you can see the overall setup, you have the switch, you have the Arduino board, you have the microcontroller, and this is the rack and pinion arrangement that he did for making this actuation on the movement, on the translational motion of those kind of splitting resonators. So when you have the two functionalities combined together, that is the switching as well as the motor movement, then you have two complementary antenna responses, the tunable notched response as well as tunable narrowband response. And this is, as I mentioned, one of the worker was a BTech student. Recently, just last week, this paper is published in IEEE Explore. Now it is available in TAP magazine, a multifunctional antenna for cognitive radio applications, where we have used the varactor diode also along with the splitting resonator. This varactor tuning on the SRR actually gives the further frequency tuning, continuous frequency tuning for the resonance frequency. So this is the expression 12 number A and 12A and 12B. This is IEEE proof I have taken. So you please follow that article if you are doing work in this area. And the antenna is microstrip fed and microstrip to slot transition, and this is the radiating part, and these are the varactor controlled SRR. So varactor diode is loaded inside the SRR. Here is the symbol, and there are some bias pads, inductors, RF choke, etc. for actuating the function. And this is some theoretical calculation and the measured results of resonance frequency. You can rely on either of these two equations, where VR is the bias voltage. So as you change the voltage, the varactor capacitance changes, and because of that, resonance frequency has a very smooth variation. As you can see over here, resonance frequency has a very smooth variation. And this is the fabricated prototype of the antenna. The equivalent circuit I already explained. And as you can see, the same antenna gives you two different set of functionality. One is the frequency notch reconfiguration over such a wide band, almost 3.5 gigahertz band. It is never reported earlier. And for the second configuration, the narrowband tunability is also available in the same 3.5 gigahertz for using those varactor controlled splitting resonator for different bias voltage, which causes the change in the capacitance. And this is the for narrowband response. Sorry, this is for the narrowband response for three cases: 1.1 gig, 700 megahertz, and again 1 gigahertz. So you will see a very smooth transition or control of your narrowband frequency, which is actually the communication frequency for the purpose I talked about, that is the cognitive radio. Further work is going on in this direction. This is the experimental setup we did at SAC Ahmedabad. This is the anechoic chamber of the SAC. I'll not go into details further because I have to have some time for discussion. This is the recent concepts that we have used for 5G application using the step impedance resonator for MIMO. Here it is, these resonators are also sub-wavelength resonator, like your metamaterial kind of resonators. So with this, with due acknowledgement to all my collaborators, I conclude my talk. Thanks to the different centers of ISRO, DST, ACRB, who are having a project with our group. And of course, I have very good rapport with NRSC, SCL Chandigarh, and other places, Royal Military College of Canada, my alma mater, University of Calcutta, at Radio Physics and Electronics, IIST Trivandrum. We have a strong relation with them. And then NIST CSIR for certain work, dielectric resonator based work, we do handshaking with them. And my IEEE organizational units. Whatever I talked about is contribution of an array of students and also the collaborators. Some of them are scientists now at ISRO and doing higher studies abroad, like Rajesh, and Shivom is doing higher studies at Germany. Another student is a faculty member, and others, some of them are still with my group. So in this, I come to the conclusion. The talk is based on some of the published articles, and finally, those articles are culminated in a book, which is published in last year with Taylor and Francis. So this is the end of my talk, and for any queries or if you are looking for any opportunities, especially for the students, feel free to write to me. We take JRF, SRF through projects and our institute projects, and I have PhD and postdoc position in my group. So I'll come to, that's it. Thank you very much once again for giving me an opportunity to talk to this prestigious podium of AIST ATAL. Thank you very much. Yeah, I'm very happy to address any queries if you have.
Thank you, sir.
Yeah.
Now platform is open for participants. If any queries are there, you can ask.
Sir, how you have calculated the C pool in your transaction paper?
Okay, I'll go to that slide and explain. Okay, do you see my slide still? Can you see my slide?
Yes, sir. Yes, sir.
I'll initially tell from here, maybe I'll directly go to, yeah. So here the C pool calculation is given only by an expression because it involves the calculation of effective epsilon, right? Epsilon effective, as you can see, it involves some detailed calculation of some elective function, and V naught, which is basically velocity, effective velocity, considering the dielectric critical, and Z naught. But Z naught is again calculated by this expression, 120 pi by square root of epsilon effective into kk. So these are the elliptic functions. Actually, the basic idea of calculation of C pool is you need to think of just, I'll go to full slide again so that I can draw something here. The basic idea, you have a SRR which is like this. I'm just drawing a square shaped one. Right, this is a outer ring and this is the inner ring. So your question is C pool, but your main question, I believe it should be, how do you calculate the capacitance? So if you can calculate the per unit length capacitance, then you can calculate the capacitance. So this model we are comparing with a coplanar strip line model. You have a dielectric, which is this is the dielectric. And on top of that you have the metal. So this is the metal. Okay. So in our case, SRR was the metal, right? It was on a dielectric again, not a problem. So we want to calculate the capacitance per unit length. When we want to calculate this capacitance per unit length, first of all, we need to understand how those capacitance are coming into picture. If I take a cross section, I'll get a capacitance like this. calculating this capacitance is not straightforward because this is the dielectric and you have metal over here and you have metal over here. So how is the field? Field, you can have different kind of fields. You can have a field from this to this. You can have fringing field like this. You will have more field through the dielectric. So considering all this field, you have to see the formation of this capacitance. And this C-pool formula that I am showing over here in the transaction paper, because this is a screenshot from the transaction paper, snip from the transaction paper. Its reference is the micro solid state circuit designed by Val and Bhatia. Please go through that and follow these steps one by one, then you will come to the exact formula for the calculation. And if you see that if sufficient information you are not getting, then this paper will be referring to few of our previous papers. Please go there, you will get all the steps for calculation of the C-pool. Is it okay?
Yes, sir.
Yeah.
Sir, one question from Narayan Rao, sir. How the lump parameter are represented for the size of 20 mm cross 20 mm cross 1.6 mm?
Please repeat it again.
How the lump parameter are represented for the size of 20 mm cross 20 mm cross 1.6 mm? They asked some question in the chat box.
Related to which slide is it possible? Then I can correlate actually. 20 mm by 20 mm. Is it related to any design or anything? Or you can.
Sir, if you are there, you can ask this question.
Sir, good afternoon, sir.
Please.
Sir, I want to represent a sheet a size of 20 by 20.
Oh, fine.
And,
so it is not related to any of my slide, right?
Yes, sir, it is related, but generalized I want to know about.
Okay.
For example, in a microstrip, you want to take some patch on a substrate. So how do the complete one? Later on, we'll go with sections or line or adding, slotting. This all is in the next part. What I want to know is very beginning when I take some sort of a dimension on a patch on a substrate. So what exactly it resembles this circuit? How do we predict that this particular circuit?
Is it for radiation application or it is?
Yes, sir. Radiation application for UWB or else that is depends. Depending upon the frequency, our LC parameter, RLC parameters will keep on changing.
Okay.
You please tell me for the high and low frequencies also, sir. Like cutoff also. Like if it is like the one particular frequency, this RLC will behave in such manner, and the above the that particular frequency that is going to the FR2 or the higher frequencies, these will vary. I know that, but exactly how do we represent these in a lumped pyramid? That is
Yeah. So
questions.
I get your question. Your question is a very generic one, not very focused. So I'll try to understand the thing and I'll try to give. So first of all, depending on the structure, because you said transmission line, planar transmission line, and then you said microstrip, and you said ultra wideband also. So it can be microstrip, it can be CPW. For some application, it can be slot line type of structure also. So depending on the structure, first we need to understand the modes. For example, the mode in CPW and mode of microstrip will not be same. The amount of fringing will not be same, depending on the structure. So once you know that, there are some techniques by which you can actually cluster you can divide your circuit into multiple subsections, the way we did the equivalent circuit. So in that way, each of that section, but when you can apply the equivalent circuit concept, that has to be understood. The concept is when our section is very tiny compared to wavelength, then only we can apply the equivalent circuit idea. So in that way, you can do it. And other part of your work was probably you mentioned some 20 mm by 20 mm and some, I think, vertical dimension you mentioned. If that is the patch dimension, then depending on what exactly you are doing with that patch, if it is an antenna, then probably not always we need to apply the equivalent circuit concept on antennas, and only when it is useful, then only we go for circuit. Otherwise, ultimately antenna is not a circuit. We represent it by a circuit for our advantages for certain application. So again, there are some references for that, for calculation of the the equivalent parameter. So maybe you can follow some of those references. As I mentioned, Bhal and Bhatia and other references are also there. So that's what I can answer at this stage. If you have a very pinpointed question, please ask later on offline or anyway, then we can probably discuss. Yeah. So this is my generic answer to your question. Thank you, sir. Thank you. Yes.
Other participant, if you have any question, you can ask. I think there is no more question. So you can conclude, Anil.
Yeah. So, first of all, thank you, sir, for giving us such a nice information regarding metamaterial, fundamental of DNG, classification of electromagnetic in mathematical, based on the mathematical model, regarding tenor antenna, energy density, group velocity, SSR, notch filter, evaluation of multifunctional antenna and wideband antenna. So we have received in this talk varieties of information from you. So thank you very much, sir, for coming and accepting our invitation. And
yeah, it is a pleasure.
Thank you, sir.
Thank you very much, sir.
Yeah, so thank you all, Dr. Mishra, Dr. Soni, and all the other organizers. It was a pleasure. And please ask the participants to feel free to email me if they have any further queries. I'll be very happy to address any queries. And I wish you all the best in all fronts in terms of COVID and other thing also. Thank you all.
Yeah. Thank you, sir. Thank you.
Bye.
Bye. Okay, dear participants, we will meet at 2:50 p.m. for the third session. Our session will start at 3 o'clock, sharply 3 o'clock. So you join at 2:50 p.m. so that we can start the session at time. And Mr. Dhariwal will be the speaker for the third session on a flexible and bearable antenna. So there is one request that you can turn off your camera while during the session. We just request to turn on the camera for taking the photographs. After that, you can turn off. You can switch off your camera. No need to turn on the camera continuously during the session. Okay. Thank you very much. You can fill the feedback and then you can take your lunch. Thank you.
Thank you, sir.